Okay, so for the ratio test, I've defined it, and now let's look at an example. So let's test the convergence of this series given here, which is the series involving n to the n divided by n factorial. So what we want to do is we want to compute the limit as n goes to infinity of the magnitude of ratios a sub n plus 1 divided by a sub n. So this is going to equal the limit as n goes to infinity. Here the absolute value isn't necessary. All these terms are positive. So we have the n plus first term is an n plus 1 raised to the n plus 1 power divided by n plus 1 factorial. And now instead of dividing by a sub n, I'm going to multiply by the reciprocal, which is n factorial divided by n to the n power. Okay. So how do things simplify here? Well, for the n factorial over n plus 1 factorial, just about everything gets wiped out except for the n plus 1 in the denominator. Now, since there is an extra n plus 1 in the denominator from the factorials, well, that's going to cancel with an n plus 1 that's in the numerator. So hopefully you can see that, and I guess maybe let me write this out explicitly so that it's clear. So we're going to cancel, so we're going to have an n plus 1 raised to the n power times an n plus 1. Okay. That's how we'll write the n plus 1 to the n plus 1, divided by the n plus 1 factorial. I'm going to write as n plus 1 times an n factorial, and then times n factorial over n to the n. So now we can see that this guy cancels with that guy, and this guy cancels with that guy. And now what's left over is two things being raised to the nth power. So now we're going to be looking at the limit as n goes to infinity of n plus 1 over n, all now raised to the n power. And so what is this? Well, let me write this in a different way. Let me write this as limit as n goes to infinity of 1 plus 1 over n to the n. Now, if it's not clear to you, we can go through the what's required in order to use L'Hopital's rule, which would be to take the natural log. I mean, here we basically have a 1 to the infinity case. And of course you can use the L'Hopital's rule after taking natural log, but if you remember, this is actually equal to e. And of course e is greater than 1, so since our ratio here is greater than 1, we conclude that the series diverges by the ratio test. Okay, so our next example is this series n squared over 2 to the n, and we want to determine convergence. So, again, we just simply look at this limit as n goes to infinity of an absolute value of ratios a sub n plus 1 over a sub n. The same thing we've done previously, which is to, again, absolute value is irrelevant here. I mean, basically absolute value will usually just get rid of this minus 1 to the n or n plus 1. In this case, we just have, so the n plus first term is n plus 1 quantity squared divided by 2 to the n plus 1. And then we want to multiply by the reciprocal of a sub n, which is 2 to the n divided by an n squared. Okay? So, in trying to compute this limit, certainly the 2 to the n over 2 to the n plus 1 cancels so that we have a factor of a half. So we can actually take out that factor of a half and write it in front of the limit symbol. So we have 1/2, the limit, as n goes to infinity, of n plus 1. Right, now we can actually group the n plus 1 over n. I mean, we can group it squared, okay, like this, and basically determine the limit of the n plus 1 over n that's in parentheses. And of course, as n goes to infinity, we have just the ratio of the n terms in the numerator and the denominator. This is 1, and 1 squared is 1. This limit turns out to be a half. This is, of course, is less than 1. So we conclude that not only does this series converge, it actually converges absolutely. So we state this series. And whether we state absolute convergence or convergence, we're still correct. I'll just state that this series converges absolutely. By the ratio test.